Good morning, Prof. Good morning, colleagues. Good morning, everyone. It is 10:15 and we are in technical session 6 of the World Forum for Women in Science. I think I will get started if all my speakers are here. Dr. Yassin, can you indicate if we should get started? Okay, I think we will get started. Prof. Okay, everybody, welcome to technical session 6, materials and engineering. And I hope so far everyone has been benefiting from the sessions that we've been having in the World Forum for Women in Science. This morning we have a lineup of 4 speakers. We have Prof. Goma Ali, yours truly, Marvadine Singh Wilmot. We have Dr. Kabira Izairi, and we have Miss Ibtihaj Sube. And we begin with our first speaker, Professor Goma Ali. Professor Goma Ali is an assistant professor of chemistry in the Faculty of Science at Al-Azhar University in Egypt. And Professor Ali's talk is entitled Low Cost and High Performance Asymmetric Supercapacitor. Professor Ali, over to you.
Thank you so much, Professor, for nice introduction. Let me start sharing my presentation. My screen is shared by, can be seen by you now?
Yes, it can be seen, Prof. Let me just indicate that we have 15 to 20 minutes in this presentation. Thank you.
Okay, thank you so much. Thank you so much for your nice introduction. Thanks for the organizing team for this World Forum. And special thanks for Professor Amal Amin and Dr. Suhad Yassin for the invitation. So now let me start my presentation for today, which is entitled Low Cost and High Performance Asymmetric Supercapacitors, Converting Waste to Wealth. Okay, actually, let's start by what is the supercapacitors, or what are those supercapacitors? Supercapacitors are alternative energy storage devices. They are some device such it's close to or similar to our the battery which we use in our daily life, our handphone battery or mobile phone battery, laptop battery, or any kind of batteries. But these are alternative energy storage devices which can store electrical energy. More electrical energy can be stored, and they have higher power density than battery, and they have fast charge time, and they can survive, or they have long lifetime. So these supercapacitors can be applied in many applications in our daily lives, including electric vehicles, household electronics, emergency door in airplanes, and in motherboard in PC, or any kind of machines or any kind of device that need electrical energy. The supercapacitor, the material used to fabricate or to design these supercapacitors, it could be two main categories of the material, and based on this material, the supercapacitor can be classified into two main categories, which are electro-double layer capacitors and, on the other hand, pseudo capacitors. In electro-double layer capacitors, the charge accumulate on the surface of the electrode material in a form of double layers. That's why it's called electro-double layer. And the material used for this kind of capacitors or supercapacitors include most forms of carbon material, including activated carbon, C60, graphene, carbon nanosphere, carbon nanotube, carbon dots, or all those carbon-based material. On the other hand, the pseudo-capacitors, the electrically charged stored in the material based on Faradic reaction or based on electrochemical reaction in the material itself. And these materials include metal oxide and conducting polymer. Metal oxide such as manganese oxide, cobalt oxide, ruthenium oxide, and so on. And the polymer could be polyaniline, polypyrrole, and polythiophene. So this various material can be used to fabricate or to design the supercapacitors. But unfortunately, the preparation cost of these materials is extremely high or quite a little bit high. So we have to find alternative sources or preparation methods to find a low-cost material to replace these materials, or maybe we have to find another sources we can obtain this material in low-cost or more cheaper way. On the other hand, our environment the world suffer from a serious problem, which is accumulation of the waste, especially electronic waste in our environment. According to EPA, American Environmental Agency, around 160,000 tons of the spent batteries accumulated in our world per year. Or basically everybody in the world use around 8 batteries in a year. So from this amount of usage battery source, we have a huge amount of the spent batteries, which is electronic waste accumulated in our world. And unfortunately, the possible ways to handle this huge amount of waste is just landfilled or integrated. So we thought that we can recycle this material or this waste into valuable material, and we could use this material in fabrication or preparation these supercapacitors. So by looking to this spent battery, which is here which I'm showing only one kind of this spent battery, which is zinc carbon battery, or we call it dry cell or dry battery. This dry material, this spent material, dry cell, has a lot of amount of manganese precursor or manganese source. After it's disposable or we use it, it still has a lot of amount of manganese and plus carbon and stainless steel or and so on. So our target is manganese. So we had recycled this material into valuable material. So basically, we started with zinc carbon battery. We dismantled it into simple components, stainless steel, plastic. This is not useful for our study, but the powder inside, which consists of carbon and manganese oxide, by using simple grounding, sieving, washing, and drying chemical methods, we obtain the solution contain the manganese species disposed in acidic solution. And by applying electrode deposition technique for this solution, we could successfully obtain manganese oxide, MnO2, in nanoflower morphology, as we can see here from this image. According to this chemical formulas or chemical reactions, the manganese species in this zinc carbon battery converted successfully into pure and high porous structure of manganese oxide in very interesting morphology, which is nanoflower morphology. As we will know later, this morphology is successful or is desirable morphology for the supercapacitor application because it allows the ion or the electrically charge to accumulate on this highly porous surface. The PSM here, it shows this one on the left-hand side, showing the PSM morphology of the spent battery powder itself before conversion. So we successfully compared this aggregated particle from mixing from a lot of component into pure manganese oxide form. And this is the X-ray powder diffraction for the dry cathode powder, which is a mixture of a lot of many species of manganese oxide species. But after conversion into MnO2 or after electrodeposition, the manganese oxide nanoflower, the XRD shows the pure and pure form, pure phase of MnO2, and which has high full width at half maximum, indicating the nano structure material obtained. By testing the electrochemical behavior of this manganese oxide or this manganese oxide nanoflower recovered from or recycled from this spent battery, the cyclovoltammogram here showing enhancement on current density, showing that a lot of electrical charge are accumulated on the surface of electrode material of this supercapacitors compared to the precursor material, which is dry cathode powder. Around a lot of enhancement occur, and we can see that in the calculator later. Also, by testing the charge availability of this material, it's showing the linear behavior of this manganese oxide. It could be charged and discharged for a longer time, for a wide potential from 0 to 1, and at different current density of 0.5, 1, 2, and 3 ampere per gram. And by calculating the specific capacitance of this material or this electrode, it shows around 200 farad per gram electrical charge accumulated on this electrode material, which supports their application as supercapacitors electrode material. So this is the first study. Second study, we use the spent cathode battery powder, again the same precursor, but we obtain the manganese oxide by different ways. The previous study, I think, published in Material Research Bulletin. By another study in, I think, Ceramic Internationals, we used another technique for conversion this spent battery into manganese oxide using cyclic voltammetry technique by applying cyclic voltammetry, I think, around up to 1,000 cycles. So this spent battery powder, which is mixture of zinc oxide, manganese oxide, is successfully converted into manganese oxide, also nanoflower morphology. And here also same, we converted this aggregated particle of manganese species into nice morphology and well-ordered structure of manganese oxide species. Again, also by testing the electrochemical performance for this material, showing enhancement in the charge accumulation from cyclic voltammogram and from galvanostatic charge cycles. And here the specific capacitance obtained for this material is around 300 farad per gram accumulated on the surface of this electrode material. In these two previous examples, we prepared the manganese oxide in a pure form, pure MnO2 structure from spent battery powder. Another method, we incorporated this manganese oxide MnO2 structure with another carbon material, which is graphene, to study the synergetic effect of these two materials, manganese oxide, which will, as we classified previously, which will work as pseudo-capacitance material, and graphene, which will work as electrodouble layer capacitance. So we want to study the synergetic effect of using these two materials as a hybrid material for fabrication of supercapacitors electrode or fabrication the supercapacitor. So in this study, we use the mixture of manganese species from spent battery and graphene oxide, and applying the cyclic voltammetric conversion to study the obtained structure. Here we successfully obtained the manganese species, manganese MnO2 species, distributed on the surface of a graphene sheet, as we can see here from the VSEM image. Here is a sheet structure of graphene, and here is a manganese oxide species. And this is a composite of both materials showing the distribution of MnO2 species on the surface of graphene sheets. And here's a Raman spectra for the pure MnO2 showing the band of Mn oxygen bond around 500. For the pure graphene showing the most characteristic bands, D and G bands for the graphene structure or the most carbon material structure. For the composite showing both peaks for graphene, D and G band, and at the same time showing the characteristic peaks of manganese oxide band, showing this indicates the incorporation of these two materials in one structure. And by testing or evaluation the supercapacitance behavior of this material, actually the composite structure of the hybrid material manganese oxide and MnO2 showing increment of the electrical energy stored in the supercapacitor even more higher than the pure manganese oxide form. As we can see here, the cyclic voltammogram showing a wider area under the curve, indicating the high amount of electrons or of ions stored on this material, and also showing wider discharge time, indicating more electrical charge. And by calculating the capacitance or specific capacitance of this hybrid material showing around 500 farad per gram, which is more than double amount of the electrical charge or the capacity of the pure MnO2 structure. So far, around more than 3 studies showing the excellent conversion of the spent battery powder into pure MnO2, and this MnO2 could be used successfully as supercapacitor electrode material. So we want to compare this MnO2 obtained from the recycled waste or from the waste source or by recycling technique with MnO2 structure obtained from chemical source. We want to compare the behavior and purity and another characteristic of these two materials to compare which one is better. I mean, this material obtained from waste source or obtained from the chemical ordinary source. So we applied the same technique, electrode deposition technique, on a solution of KMnO4 as a manganese source. And we successfully obtained the MnO2 structure in nanoflower morphology, as we can see here from this both same image, by applying advanced technique and potential technique, both electrode deposition techniques, but one is applying fixed current and one is applying fixed potential. And successfully, by using both techniques, we obtain the nice morphology of pure MnO2 structure. And here also by X-ray diffraction showing the pure MnO2 structure, actually deposited on a stainless steel substrate. So we can see some peaks for stainless steel substrate. So by testing the electrochemical behavior of this material, also the manganese oxide obtained from chemical source have the same behavior or almost very close behavior in terms of cyclic voltammogram and charge time is very close to those obtained from the manganese oxide obtained from the waste source, showing around 200 farad per gram specific capacitance. And here's interesting is showing a highly stable structure of MnO2, showing that by testing the stability up to 5,000 cycles, I mean 5,000 cycles using charging and discharging the supercapacitor or the primary lab-made supercapacitors. It could be used for 5,000 cycles or 5,000 times, and still has more than 90% of its original capacitance. In simple way, if we have this supercapacitor and we charge it and we use in our device, in our phone or whatever the device, and we charging and we use it to power the device, and we charge again and use to power the device again for 5,000 cycles, it will still maintain more than 90% of its original capacitance, which this phenomena we cannot see in the ordinary battery. Actually, after 1 or 2 years, around 500-600 times of using, based on we use it for one time per day. I mean, it's charged and discharged for 1 time per day. So around 600 or 700 times of using, it will be almost we feel it's die or it's lost a lot of its power or its capacity. And this is in this point, the supercapacitor is very interesting device compared to the battery, especially in this point.
Prof, can you wrap up in 3 minutes?
Okay. I think we can skip some of this. So we can conclude our study. So manganese oxide in nanoflower morphology, it could be successfully obtained from by recycling technique or by recycling method by using electrodeposition technique to be precisely to be fabricated from spent battery powder. So we can successfully recycle the spent battery powder material into promising material, which is MnO2 form, either in a pure form or incorporated with another carbon material or even polymer material or even to whatever the hybrid composite we want. And this MnO2 obtained either in a pure form or in hybrid form, it works successfully as a promising candidate for the supercapacitor's electrode material. So some awards and exhibition, and here some of my collaborators through the world. I have some collaboration in USA, Singapore, Australia, and definitely Malaysia. And this is some of our lab, electrochemical testing lab and and synthesis lab. And this is actually my recently, because most of my work based on recycling technology. So this is my book titled Waste Recycling Technology for Nanomaterial Manufacture, which is published recently by Springer Nature. And thank you.
Thank you very much, Prof. Ladies and gentlemen, we are looking forward to a robust discussion at the end of the talks by all the speakers. So I invite you to put some comments in the chat or have your questions ready for when all speakers have presented. So Prof is going to close his camera on share so that I can thank you once again, Prof. Low cost and high performance devices are certainly essential in developing countries like yours, and mine, like ours, and in fact in the world. And so now we want to, I am going to share my screen, and I am going to speak in the next paper, that is my talk. I am Marvadine Singh Wilmot, like I said before, and I am a lecturer in the Department of Chemistry here at the University of the West Indies, and that is in Jamaica. Prof, can you or some other colleague please indicate to me if you are seeing my screen?
Yep, we've seen it.
Thank you. So my talk is entitled Exploring the Synthesis and Potential Applications of Lanthanide 3-Coordination Polymers and Metal Organic Frameworks. And just to give us some perspective in terms of where I am coming from, I am here in Jamaica, that is our island there, and we are here in Duhok, Iraq. So we are in the Caribbean, about 7,000 miles or so away. If we had one straight flight, it would take about 14 hours, but otherwise you travel for over a day. We are world famous for our music. We have Bob Marley, we have and our sports. Most of you would possibly also have heard about Usain Bolt. So our athletes are also world famous. Let me just get my pointer here. We also are famous for our climate, of course, and beautiful beaches like these ones here. And water features like Dunn's River Falls are also world famous. So as soon as the pandemic is over, we're looking forward to more of you coming over here to enjoy our beautiful country. Our university is a regional university serving the Caribbean. It's the largest and most long-standing university in the English-speaking Caribbean. We have four campuses serving 16 countries, highly diverse student body and faculty. We would say the world is represented at the UE. This is taking you a little bit into my department. Here is the chemistry department, a little bit more inside my lab. We, like many developing countries, have limited resources for science, but certainly our commitment to doing science and the talent that we have is strong. So we are doing science. We are doing what we can do well. We are making new materials, growing single crystals, using various techniques, slow evaporation, vapor diffusion setup is what I'm showing here. We do hydrothermal synthesis in pressure vessels like these, and we do what we know and do best. And for me, I'm a lanthanide chemist, so I've been studying the lanthanides, which are the elements here from atomic number 57 to atomic number 71 for a very, very long time now. And so we are interested in the lanthanides, of course, because the lanthanides have numerous applications in many future and current technologies. For some reason, my screen is frozen. I am unable to move. Not sure what is happening here. Okay, there we go. So we have applications as MRI contrast enhancement agents, as phosphors. Europium, for instance, is featured in the Euronote as a security feature, biomedical probes, and in catalysis. I mean, if you take up an iPhone and look at how many lanthanides are there, from the color screen to the circuitry to the speakers, it will let you understand why we have to study these materials. And in Jamaica, we are closely connected to the lanthanides because rare earths, you know, when the lanthanides are combined with yttrium and scandium, we call them the rare earths based on the mineralogies. So they have been found in, I would say, significant portions. In fact, there was a commercial venture to explore extraction of lanthanides from the bauxite waste. And bauxite is a mineral deposit. We mine bauxite from which aluminium is extracted. So we've been making coordination polymers from lanthanides. A coordination polymer is just metal ions or metal ion clusters that are bridged by organic ligands. And we can bridge in 1 dimension, 2 dimension, or 3 dimensions. And a special class of coordination polymers, which we are most interested in, are the metal organic frameworks. They have cage-like topologies. So we have the organic building units depicted here and the inorganic units as the nodes, and we can bridge these up into a cage-like topology, unusual, enhanced porosity, and I'm showing one here, which shows you the metal nodes and the ligands that are bridging. The yellow sphere is showing you the pores inside this particular framework. So the coordination polymers, and indeed anything that has clusters of metal ions, have numerous advantages, and metal ions clustered and complex to organic ligands. So these advantages take advantage of the inorganic and inorganic components and the interactions between them. And there are many applications of MOFs and lanthanide MOFs. So from gas storage to separation and purification and sensing, which is what we are particularly interested in. These applications align with the global sustainable development goals. You know, we can have envisage applications from climate change. These things are able to trap and store greenhouse gases like carbon dioxide, in renewable energy, in clean water and sanitation. So reticular synthesis has evolved as a means of judiciously designing these metal organic frameworks. So we are combining judiciously these building blocks into predetermined ordered structures by strong bonds, and structures with the same topology like this series here are said to be isoreticular. So you notice we are changing the organic linker and changing the size of the pores as we go from one to the next, and the chemistry that you can do inside here is also different with and related and can be systematically varied within a series. But there are challenges to developing lanthanide MOFs. So the lanthanides have a spherical crystal field, and it's less predictable. Their coordination geometry and coordination behavior is not predictable. And so we need to have many more of these compounds made, characterized, and their structures deconstructed in order to extract strategies that can inform rational design and synthesis of targeted materials based on lanthanides. And our aim, therefore, is to make these lanthanide compounds and study their potential as functional materials. We started in the early days by just putting together two lanthanide ions into molecular systems and characterizing the interactions between the two using luminescence spectroscopy. And of course, my talk this morning is not centered on this, but certainly it gives us some context for where we're coming from, and it sets the framework. We evolved from the interaction between two metal ions to the interaction in polynuclear clusters or polynuclear compounds. Again, these were not coordination polymers. These were isolated molecular systems, but they gave us the chance to establish the behavior within an isolated system and the nature of the interactions between lanthanide ions in an isolated system. This work was well received in the literature. So we did different types of clusters where the lanthanides were connected by various what we call supramolecular glues. Those are small ions that connect the lanthanide ions. And we studied the impact of using various supramolecular glues like oxides and hydroxides to connect lanthanides in various geometric predispositions. And we were able to do some calculations, in fact, that allowed us to calculate and to determine the contribution to the interaction between, say, europium and another lanthanide, dysprosium, that are connected by hydroxide units. And we were able to calculate the contributions from the energy transfer rates. I mean, if you look, just share in a few moments the decay curves, we were able to capture what's going on between lanthanides that are communicating within a cluster. That's in the fast range here. And here on the longer side, the longer decay rates, you were seeing what was happening between lanthanides that were in different clusters communicating via intermolecular interactions. And we defined these. In conclusion on that section, we defined and concluded that supramolecular glues like oxides and hydroxides in these clusters and the bridging modes, the mode in which they are bridging influences the strength of the coupling interactions among lanthanide ions. And we were also able to show that the bridging ligand's dipole moment was more important than the polarizability, and that energy transfer involving these lanthanides is predominantly by dipole-dipole interactions. So as I said before, we calculated the electronic coupling constants and showed that the coupling between the lanthanides would increase with the number of lanthanides that were attached to a single supramolecular glue moiety, like a single OH minus. So having done that now, we were able to go on to the coordination polymers and MOFs. And I will just summarize some of our findings here. We started with some simple coordination polymers. These were linear coordination polymers, the crystal structures we defined, and we saw they were one-dimensional chains. And we did some luminescence work to show, in fact, in this one, we have lanthanide ions, erbium, and they were bridged via sodium ions. And we were able to show that the sodium would interchange, and there were some dynamics between the sodium ions and the lanthanide ions interchanging positions. But then the framework materials we went into, which is what I want to focus on now. We have used a variety of ligands, and I'm showing some of them here, We've used a variety of rigid aromatic carboxylate ligands, and these have limited coordination chemistry with lanthanide ions. We were able to search the Cambridge structural database. So because of that, the chances of obtaining novel coordination polymers and MOFs was great. If you notice, we are choosing bi and tri-dentate ligands because these can bridge multiple lanthanide ions, leading to frameworks that have high dimensionality. And the ligands contain these carboxylate groups, if you notice, because these are hard Lewis-based sites and they would bind strongly to the lanthanide ions, which are hard Lewis acids. And the carboxylates have versatile coordination modes. So, you know, multiple structures can be envisaged with the same ligands. And if you notice also, the ligands are related. So in one case here, we have benzene dicarboxylic acid, then we change one functionality to the hydroxy, and we put on the nitro group. And then in these two, we were looking on the tetrahalo, because these offer the possibility for halogen to halogen interactions. And here we are introducing systematically varying the properties of the ligands. Okay, so those are some of the reasons why we chose those ligands. Here are some of the results. We have named all our MOFs UII for University of the West Indies, UII MOFs 1, 2, and so on. So we have made a number of these with different aesthetically pleasing structures, and part of the program is to solve the crystal structures of these MOFs. So we are showing here UII MOF 1 up to UII MOF 19, and I will zoom in a little bit on some of these in subsequent slides. So if we look on UII MOF 1, and what we have is a framework structure with benzene dicarboxylic acid, and the asymmetric unit is what we are showing here. And this is made under hydrothermal conditions, solvothermal to be exact. And it forms, like you can see here, a three-dimensional pillared framework. So inside here, you have the two-dimensional sheets that are pillared by the terephthalic acid, terephthalate linkers. We were able to reticulate, so we deliberately now go in and change the nature of those linkers, and found that we could make UII MOF 2 if we change the linker, extending the linker chain using biphenyl dicarboxylic acid. The nature of the framework structures, all featuring this brick wall, this two-dimensional inorganic brick wall motif. And basically, this is entirely made out of the building units, these building units, which we call the secondary building units. So since all of these structures were showing this TBU feature, as we call it, this tertiary building unit feature, we took advantage of that to make even more, and we're able to change the functionality in the linker. Again, we were able to form UII MOF 3 and UII MOF 4 when we again continue to change the functionality. And we reported the first family of isoreticular Ln-MOFs. See, the thing is that previous to this study, the ability to reticulate, because of the variable coordination chemistry of lanthanides, the structures that people would get are unpredictable because lanthanides exist in variable coordination modes. They were stable. And so it was very difficult to reticulate. So we showed with UII MOF 1 to UII MOF 4 that we were able to systematically vary the structure of the linker, extending that pore size by extending the linker, and changing the electronic properties of the MOF by changing the electronic properties of the linkers. And we reported that one well received. The other structures I wanted to show you were with the nitroterephthalic acid. We got a series of compounds when we go across the lanthanide series, lanthanum and cerium would give us UII-MOF 7, and neodymium would give us UII-MOF 8 and UII-MOF 9 under different conditions. So slow evaporation conditions would give us UII-MOF 8, but hydrothermal conditions gave us UII-MOF 9. And UII-MOF 10 we got here with samarium to erbium. When we go to the tetrabromo terephthalate, so we're substituting now and using tetrabromo terephthalate instead of the nitro terephthalate, we form UII-MOF 11 under slow evaporation conditions with lanthanides from lanthanum to thulium. Sorry, with lanthanides from lanthanum to dysprosium, and with lanthanides from holmium to lutetium, we form UII-MOF 12. When we change the tetrabromo to tetrafluoro, we formed different structures. In fact, over here, I'm showing you the tetrafluoro structures. Tetrafluoroterephthalic acid gave us UII-MOF 13 and UII-MOF 14 for the very small lanthanides, ytterbium and lutetium. And we were interested, like I said, in these tetrahalo ligands because of the abilities for halogen to halogen interactions, which are still being exploited in supramolecular chemistry. And I'm showing you what we found when we studied these structures, the tetrabromo structures. You can see here the bromine to bromine distances as we vary the lanthanide size. We go from lanthanum large to dysprosium small. The bromine to bromine distance would get smaller. So there's a relationship between the size of the lanthanide and the strength of the interactions between the interhalogen interactions in these MOFs. And there were some other very nice structures with the tetrabromide. The holmium to lutetium featured some very nice, aesthetically pleasing, this sort of water cluster, which was trapped in the pores of this MOF. This we call Star of David water cluster, which was encapsulated, which was encapsulated inside the framework. This was a holmium octa-aqua cation. These were trapped inside the pores of the framework. With the tetrafluoroterephthalic acid, I told you that we get UII-MOF 13 from lanthanum to thulium, and UII-MOF 14 we got with lutetium and ytterbium. But what do we do with these structures once we've made them? I said to you we were interested in the sensing properties, in using these MOFs to detect metal ions and explosive nitroaromatics, which are toxic, of course, you know. So we explored in all our MOFs, but I just show you a couple here because my time is up on me. I should be wrapping up in a few. We explore the sensing properties, and I'll just show you in the presence of UII-MOF 11, we're sensing iron and copper. In fact, you see the quenching efficiency is great in the presence of iron and copper. So here we have some pictures showing you we have red emission, and once iron or copper is present, the emission is quenched. And we did quite a bit of studies on exploring the mechanism of quenching and improving that we can reuse this as a sensor for over 5 cycles. So here we're showing the PXRD patterns that show that, you know, as synthesized, this is it, PXRD pattern. And with iron, after 5 cycles, you can see the PXRD pattern looking pretty much the same. And in fact, the infrared also looking pretty much the same, showing that there isn't much structural, structural change. And we looked more into the mechanism and noted an inner filter effect of these analytes on the framework. Okay, and so the sensing studies also showed that there was some amount of selectivity even in the presence of a cocktail of metal ions, there was selectivity for iron and copper. That's what we are showing on these slides. So in summary, we have synthesized and structurally characterized quite a number of polynuclear compounds of lanthanides, as well as framework materials. The tetrabroma and tetrafluoro, the tetrahalo compounds we have shown are good sensitizers for metal ions and explosive nitroaromatics. And we have shown, in fact, that the terephthalates, the hydroxyterephthalates complexes or compounds, MOFs, are sensors also for aluminum. And so I say, in summary, we have made over 19 novel compounds, and we have exerted control over the formation, and we reported the first ever isoreticular lanthanide MOFs. The materials have strong potential as sensors for metal ions and explosives, and they display tunable luminescence. And going forward, of course, we want to look at catalytic activity, gas absorption, and sensing of local pollutants. That's a view of our campus, and these are the wonderful young people who continue to empower us as we empower them. Thank you to all my students, to TWAS for funding the Royal Society of Chemistry and the UII's new initiative grant, which helps us with funding. And thank you, colleagues, for your attention. Okay. We see some discussion going on in the chat there, and we will get back to that. But now it is my pleasure to introduce our next speaker. Our next speaker is Dr. Kabira Ezairi, and Dr. Kabira Ezairi is coming to us from the Thermodynamics and Energetics Lab in the Faculty of Sciences at Agadir, Morocco. Dr. Kabira Ezairi will speak on photovoltaic energy for Canarian greenhouse. Dr. Ezairi, over to you. Okay, colleagues, I'm checking, just doing a check on what's going on with Dr. Kabira. All right. So we are not hearing Dr. Ezairi right now, so we are going to go on. I think it is wise to go on to our next speaker then. Just check in to see that Ibetihaj Sube. All right, let me do a sound check here, everybody. Is everybody hearing me? Is anybody hearing me?
Yeah, for me, it's okay. Your voice is clear to me.
Thank you, Prof. So it seems like I do not have connection. No, I am seeing Ibtihaj Sube. Thank you, Zara. I am okay. Well, Ibtihaj, could you let us know if you are hearing? In fact, I'm seeing. All right, what we shall do then. Ibtihaj, you are here. You're recorded as being here. So we're not hearing from you. So shall we have a discussion on the two papers that have gone in this section? I think as soon as our colleagues come on, we can take those papers, but it would be wise for us to make use of our time and just have a little discussion. Let's see if there are any. All right, we have there is a question here from Dr. Rana from the University of Baghdad. And Dr. Rana is saying, thank you for the interesting lecture. I have inquiry about the MOFs that you've synthesized. What is the water resistance and the thermal stability for these MOFs? So Dr. Rana, we actually did the TGA analysis, the thermal stability, and we did prove that most of our MOFs are stable over 500 degrees Celsius. And we do have a number of them that are stable in water, but so the solubility in water is actually very low. But we do need some more water studies, because there are some of them, in fact, the luminescence quenching, because OH oscillators on water do quench europium emissions, lanthanide, europium, the red emission from europium. And so there is some interaction, the nature of the interaction between the water molecules and the lanthanide, we have to investigate, but there is some interaction between the lanthanide and water. In fact, there is quenching in some of them in water, but there is thermal stability and some water resistance in terms of solubility, but the interaction in water needs to be investigated more thoroughly. Let's see, does anybody have any question for Prof. Goma Ali? I don't hear any more questions. Well, let's go back and see if Ibtihaj, sorry, is Ibtihaj Sube hearing us?
If no question from the participants, so could I ask you a simple question regarding your presentation about MOF?
Yes, please go ahead.
Okay, thanks for your interesting talk. Actually, I'm interested and I get a lot of information from it. So basically, I'm working on supercapacitor, which is basically use the material to store the electrical energy. And what I understand from MOF is it's porous material, and it has a lot of voids in the structure. So what about the conductivity of this material? It will be conducting material. I mean, it conducts the electrical current through these structures.
Yes, so we have not done any studies on that, just because we are not set up. We don't have the facility to do this testing. But there is that kind of work that's going on in MOFs for conductive materials. And there's also on the inside pores, being able to do a lot of photochemistry inside there. I mean, the reactions that there are many reports of these, but for my MOFs, I haven't done any studies on those.
Because it will, if it's conducting material, it will be a promising material also for electrical storage. So
yes. And so, like I said, this is reported, but for my materials, and if you are able to do these studies, a nice collaboration for me, because from where I am, there's so much I would like to do in terms of the catalytic work, in terms of hydrogen storage and use in a fuel cell. I have done some carbon dioxide and nitrogen adsorption isotherms, and have shown that these things can, in fact, like I said, they are stable up to 500 degrees, some of them 560 near 600 degrees. And we have done some initial adsorption isotherms to show that they can absorb carbon dioxide and nitrogen and remain stable. So, but yes, and the promise of these things in as electrical storage materials, as gas storage materials, as use as fuels in the hydrogen fuel cell, these things are under investigation, and some materials have shown a lot of promise.
Yeah, thanks.
Okay, thank you. I wonder if there's anyone from the organizing committee who is here who could advise me on what's going on with our other speakers.
I think Tihaj Subhi is appear here, so maybe It's already joined.
I see Ibtihaj. Been here for a while. I've been calling out. I don't know if there is some sound problem from Survey. Maybe there's some audio problem.
Good
Are
evening,
there?
everybody.
Oh, very nice. Ibtihaj. Very nice to have you, Ibtihaj. Okay. So Ibtihaj, everyone, is from the College, let's see, Ibtihaj is from the College of Science. No, Ibtihaj, you are from the College of Veterinary Medicine, isn't it?
Yes, I'm from College of Veterinary Medicine,
Yes.
but my special major in organic chemistry.
Right, and she's from the Department of Pathology and Microbiology in the University of Doha, Kurdistan, right here in Iraq, who are our gracious hosts. So Ibtihaj will speak about green chemistry reactions in Duhok City, part 3, optimization of rose Bengal dye concentration as oxygen quencher in the photosynthesis of benzopinacol. Ibtihaj, over to you, ma'am. Can you check if your share screen feature is on?
Okay. My presentation about green chemistry reactions in Duhok City, part 3, optimization of rose Bengal dye concentration as oxygen quencher in the photosynthesis of benzopinacol. Green chemistry. Green chemistry is a word term used to describe the development of more eco-friendly, sustainable chemical product and process. Chemical products should be non-toxic and generate non-hazardous substances. Light is regarded as a clean reagent, hence photochemistry can contribute efficiently to the growing field of green chemistry. Benzopinacol photosynthesis by photoreduction of benzophenone. The first reported photoreduction of benzophenone with alcohol by French workers in 1900. In 1920, Cohen followed the disappearance of benzophenone using rudimentary version of UV absorption spectroscopy. The classical example for benzopinacol photosynthesis by benzophenone by photoreduction of benzophenone under sunlight using isopropanol as a solvent, the time required for complete reaction more than 24 hours with 93 to 94% yield. The general mechanism for benzophenone photoreduction isopropanol to prepare benzopinacol, benzophenone under irradiated to sunlight, excited to singlet, which intersystem cross to triplet, then in a triplet reacts with isopropanol as a solvent, forming radical. The radical that forming from isopropanol as a solvent reacts with mole from benzophenone, give me mole from acetone. Under dimerization, 2 mole from radical that forming from benzophenone converts to benzopinacol as a stable product. This figure shows benzophenone excited state after irradiated, excited to singlet, which intersystem cross to triplet. The triplet energy of benzophenone is 69 kilocalorie per mole. Role of oxygen in benzopinacol yield. After irradiation, the reaction of photoreduction of benzophenone under sunlight, if this solution is saturated with oxygen and irradiated to sunlight, the benzopinacol no forming and no precipitate form. Here, the effect of oxygen in the reduce the yield of benzopinacol after irradiation benzophenone to sunlight after excited reacts with the isopropanol as a solvent forming radical. The radical that produced from benzophenone destroyed by oxygen and forming benzophenone, not benzopinacol. This is cause becomes decreased the yield of benzopinacol. Also, the radical that forming from isopropanol also destroys by oxygen and forming mole from acetone. The hydrogen peroxide that forming during the reaction also affects on the reaction, and the benzophenone here that formed in the system is not used up in the reaction. We see here no benzopinacol forming because the oxygen destroys the radical. Photolysis mechanism. In general, we have two types from photolysis mechanism. The first one is cell sensitization between two dyes process at high concentration. Here, the sensitizer excited to singlet, which intersystem cross to triplet, maybe reacts with oxygen oxidized or may be reduced. The second type of photolysis mechanism is the quenching by singlet oxygen. Here the sensitizer under sunlight excited to singlet, which intersystem cross to triplet, then reacts with atmospheric oxygen to produce singlet oxygen. Singlet oxygen here is a quenching, not involved in the reaction. Rose-Bengal as photosensitizer. Rose-Bengal is xanthine dyes since the 19th century, the structure of which has been well known, named for the so-called Indian happiness words. This is the general structure for Rose-Bengal dye sodium. This photosensitizer is red in color and related to fluorescein structure that has been important in photochemistry. Rose-Bengal triplet state is quenched by molecular oxygen with bimolecular rate constant of 2 multiplied 10 sub 9 molarity multiply second minus 1 in ethanol as solvent. And it is low triplet energy between 39.2 to 42.2 kilocalorie per mole, and for that reason could be used as a sensitizer. Dyes concentration effect on benzophenone consumption. The quantum yield of benzophenone consumption decreases when the concentration of Rose-Bengal increases. Also, the radical that forming decreases when the Rose-Bengal concentration increases. Rose-Bengal bleaching or decomposition. The Rose-Bengal bleaching or decomposition occur either under condition in which the dye is oxidized by partner ion or by oxygen. Here the sensitizer after excited maybe reacts with oxygen oxidized or may be reduced. Dye photo bleaching factors. We have several factors that affect on photo bleaching or decomposition for the dyes. The first factor is the free radical formation. Free radical formation, of course, affect on photo bleaching of the dyes. We have two pathways to forming free radical. The first one, free radical formation and the reduction condition. Here, this is the structure of the Rose-Bengal dye sodium as xanthine dyes, and the reduction condition by using Zn acetic acid, and the special condition by reflex about 24 hours. We see deionidated in the position number 2, number 4, number 5, number 7, and number 9 pentahydro. So according to this reaction, free radical formation and photobleaching appears during the reaction. Free radical formation by dehalogenation. Another pathway to forming free radical by dehalogenation. Here, this is the structure of Rose-Bengal. In first step, we see leaving iodine's atoms, and in second step, leaving chlorine atom in decolorization. This is a fluorescein sodium. According to this reaction, free radical forming and photobleaching appears. The second factor that affects on photobleaching of dyes is hydrogen peroxide concentration. During the reaction, hydrogen peroxide forming increase the concentration of hydrogen peroxide, cause decrease for dye concentration, and increase the hydrogen peroxide concentration, increase to the photobleaching of the dyes. Another factor that affects on the photobleaching of dyes is dye concentration. The xanthine dyes like rose bengal at low concentration degrade rapidly through an oxygen-mediated photoreaction which requires dissolved oxygen. And the response of rose bengal degradation is very sensitive for independent factor of the dye concentration. Aims of the study. In order to investigate the role of rose bengal as a photosensitizer in finding a fast and green chemistry procedure to synthesize benzopinacol, also to study the different concentration of the rose bengal in different experiments to eliminate the quenching effect of oxygen in benzopinacol synthesis. Benzopinacol in general, prepared by photoreduction for benzophenone under sunlight using isopropanol as a solvent. This table shows 4 experiments for benzopinacol photosynthesis. In these experiments, we see Vogel-reported experiments. We used here benzophenone, isopropanol, and we used rose bengal as sensitizer. In this experiment, the amount of rose bengal, according to Vogel-reported experiments, is 0 gram. The time required for complete reaction more than 24 hours in 92% yield. In experiments number 1, we addition amount of rose bengal about 0.001 gram. The time reduced to 4.5 hours with 86.1% yield. This reaction is followed by gas chromatography. In experiment number 2, we increase the amount of rose bengal to 0.005 gram. The yield of benzopinacol is reduced to 23.8%. When increase the amount of rose bengal concentration, the percent yield of benzopinacol that forming is decreases. So in experiments number 3, when we used 0.05 gram from rose bengal, no reaction happened, no benzopinacol precipitate, because the increase in rose bengal concentration caused decrease in the yield of benzopinacol. This 2 rows refers to the solution color at the start and solution color at the end of the reaction. The general mechanism between benzophenone and rose bengal in the reaction after irradiation to sunlight, excited, and rose bengal give electron to benzophenone, forming radical cation and radical anion. After which intersystem crossing to triplet, we have 2 paths. In path 1, when we used rose bengal in low concentration, 0.001 gram, here the role of rose bengal is excited to singlet, which intersystem cross to triplet, then reacts with atmospheric oxygen, produce singlet oxygen. So the singlet oxygen here in this step is a quenching, not effect on the reaction. At the same time, the benzophenone in triplet under dimerization converts to benzopinacol in high yield, about 86% yield, and reduce the time of reaction, because here the concentration of rose bengal quench the oxygen that effect on the benzopinacol yield and becomes decreased. In this path, when increase the concentration of rose bengal to 0.05 gram, here the benzophenone not reacted, we don't see benzopinacol, we can isolated benzophenone and detected by melting point. Here the rose bengal is converts to unknown product because we see change in color in the reaction. This is meaning the change in the major of rose bengal maybe happens in this structure. The quantitative benzophenone Analysis involved the injection of 3 standard solution,
Are you okay?
sorry, maybe.
Okay, it's back.
Okay. The quantitative benzophenone analysis involved the injection of 3 standard solution, 1, 2, and 4 microliter withdrawn from 0.087 molarity solution of benzophenone. And this figure shows benzophenone standard curve, R square closest to 1. The standard curve equation, of course, was obtained by plotting peak highest that obtained from the chromatogram as a function of concentration. The incorrected melting point for benzopinacol about 186 to 188 centigrade and agrees with the literature reported. UV visible spectrum. The UV spectrum of benzophenone that calculated in isopropanol as the solvent, the Ln-MOFs at 254 nanometer belongs to pi star of the aromatic benzene ring, and UV spectrum of benzopinacol in ethyl acetate, the Ln-MOFs at 261 nanometer belongs to pi star of the aromatic benzene ring. This figure shows the IR spectrum of benzopinacol that's synthesized. This band refers to the OH stretching that found in the structure of benzopinacol. The control experiments for Rose-Bingle photobleaching. The purpose of the control experiments here, firstly, the control experiments, just we used Rose-Bingle in isopropanol without benzophenone. The purpose of control experiments to know the effect of benzophenone in the photobleaching or change the color of the reaction. Here in the first experiments, we used 0.001 gram from Rose-Bingle in isopropanol. We see no change in color after exposure to sunlight. When increase the amount of Rose-Bingle to 0.005 gram in isopropanol, also we don't see change in the color. Increase the amount, here we change the solvent. In experiments number 3, we see here in experiments number 1 and 2, we used isopropanol as a solvent because it is as a part in photoreduction of benzophenone to prepare benzopinacol. We change it to water. After 42 hours, we see the change in color of solution from pink to pale pink. This figure shows UV visible for Rose-Bingle before exposure to sunlight, and this figure shows UV visible spectrum for Rose-Bingle after exposure to sunlight. We see here difference in the absorbance. This difference in the absorbance before exposure and after exposure due to the 9 position in the structure of Rose-Bingle, so the double bond cleavage here and converts to single bond. Conclusions. Rose-Bingle to benzophenone ratio 1 to 5,000 accelerate the time of benzophenone photoreduction to benzopinacol to 4.5 hours. The reported experiments for benzopinacol photosynthesis takes 24 hours to produce benzopinacol from benzophenone. When the Rose-Bingle to benzophenone ratio is 1 to 100, the reaction does not occur. Thanks for your attention.
Thank you very much, Ibtihaj, and for the excellent work you are doing. We must remind the audience that you are a PhD student in your program, and I think special commendations are in order for you, ma'am. So, ladies and gentlemen, I would like to thank again all our speakers. I still do not see my fourth speaker is not here. I am calling again Dr. Kabira Izairi. If you are here, please let us know. I do not see Dr. Izairi. So we are going to open the floor. We're going to thank all speakers and we're going to open the floor again for discussions. I do know that there is one question that is registered in the chat for Prof. Goma Ali. Let's just go back to that one. Prof. Goma Ali, does the cost of recycling manganese dioxide, is it significantly less than the newly prepared ones? This is from Zara. Zara Ali.
Yeah, I think yes, it should be less than the cost of the recycled MnO2 is less than the chemically prepared. Keep in mind the cost of the precursor itself is almost zero. I mean, we just collecting this spent battery from accumulation or from the waste areas. So the cost is almost zero. It's just the transportation cost. And another point, which is the impact on of environment. This recycling technology has a positive or a green impact on our environment by solving the accumulation of this waste in our environment. So by taking these two notes, actually the cost almost to be promising. I mean, it's very less cost, and the process is promising to obtain this material from the waste source instead of the chemically prepared source.
Thank you, Prof. Zara, would you like any to redirect on that one? Or I see that Prof had actually sent a reply in the chat also, which missed me, but it's good to have that voiced and shared with all listeners. Are there any questions? Any other questions? Any questions for Subhe? I'm just going through the chat here again. Wonderful. You know, these meetings are supposed to serve the purpose of connecting scientists with scientists and also sharing what we do with the world. And so this discussion between Rana and myself is leading to something here you are all seeing in the chat. So I am grateful for that, absolutely grateful, and hoping that as soon as this pandemic is over, then we can continue this science diplomacy and this movement of scientists across borders and into each other's countries and labs. Are there any more questions, ladies and gentlemen? Any more questions? Any more comments? Right. So our organizing committee here is saying you can turn on your video. You may turn on your video so we can have you. Right. That would be nice for when we are discussing. Rana, it would be nice for me to put a face to the name. So I wouldn't mind seeing your face. You can turn your video on. And we're inviting more comments, more questions to come up for our speakers. Just checking through to make sure we haven't missed anything in the chat.
I think someone is asking about sending the presentation via email. I think it's recorded. The whole session is recorded and it's available on via Facebook Live or even on YouTube. So I think this one will be useful instead of sending the PDF or presentation. Yeah, am I right?
Absolutely, absolutely, Prof. These presentations are available on all the social media platforms. Women in Science Without Borders is quite active, and so we can find these. These are available. Okay, we do have some more time in this session, ladies and gentlemen, and the opportunity for networking should really continue. And we should take advantage of this opportunity for networking and speak some more, see each other's faces, and learn some more about each other and the science that we do. Maybe even about the limitations for doing science, you know, in our country. I can tell you guys, I'm just keeping my eyes on the chat to make sure that we're not missing anybody. And your comments. Prof, you will continue to help me, yeah? Okay, so Rana is telling us that unable to turn on the camera. Oh, that's okay, Rana. It is International Women's Day. And these are some of the realities that we face. I am a mother myself, my son in the next room at school, because our schools in Jamaica are still online because of the rise in COVID numbers. So you have highlighted some of the things that have been highlighted in our sessions, and that makes a day like today so very relevant, that you are able to be here doing science with us and contributing to science for humanity while you mother and secure the future of the world. So we quite understand. All right, any more questions though, guys? We do have some time because one of our speakers is out.
I noticed something. I checked the panel list and even the attendee. So most of them, even if not all of them, are ladies. So I'm thinking about myself. I'm in the right place, or should I have to leave now?
No, yeah, you have to leave also now, Prof. No, well, some of the challenges we face as women are common to all human beings, whether you are women or not. But indeed, yeah, women in science are well represented at this meeting. Or after all, it is a International Women in Science Forum, right? World Forum for Women in Science, but it is equality for all, and so we could not do this without our male counterparts like yourself. So we are happy that you are here, even if you are outnumbered.
Yes. So I have to fight for the equality, yeah.
Yes. No, but so how about the funding for this research, Prof?
In Egypt, because my last 7 years I was in Malaysia, so the funding there is not bad, quite okay. Here in Egypt, I have around 1 year in Egypt, so the funding is quite, we can say, almost okay. We have some funding agency like in our academic of scientific research, and we call it STDF. So it's quite okay to support some research, yeah.
And how about the facilities? Like for us, we are challenged as a small island state in a developing country with resources, like most of us are and certainly the research infrastructure. We have opportunities to travel, and international funding agencies do facilitate that, TWAS and others. The Royal Society of Chemistry, Commonwealth Chemistry, these things facilitate travel, and even the university itself. But the money for equipment to build local infrastructure and in materials and engineering, and for your materials to begin to translate into economic activity, you know, the infrastructure, the equipment locally to empower local development of infrastructure, for me, is a challenge.
For me too, also it's challenging because we are in Middle East countries, so we suffer from this problem too, yeah. But we look for alternative solution by doing some collaborations. That's why I list down some of my collaborators. For example, if I have no facilities to run this test, so I just prepare the material and send to my colleagues in another country, in Poland, USA, Japan. So they do further testing and support me with some results. So we collaborate together to finalize our work or our task. Yeah. So this is a quick solution to finalize the work. Yeah. But actually we suffer too from this, from the supporting or funding for the equipment, especially equipment. Yeah.
What about the doping of these materials that you make, Prof? What about doping? I know manganese with some lanthanides even.
Yes, it could be. It could be well investigated because if we dope with some another metals or metal oxide, even it will affect the morphology or the crystal structure or increasing the band gap of the material. So by playing with this material characteristics, it could enhance the electrical properties and the storage behavior of this material. Actually, I have done so many studies about manganese oxide, cobalt oxide, graphene, carbon nanotube, a lot of varieties of material. But here in my presentation today, I focus only on one series, which is manganese oxide recycled from spent battery. But for my PhD and 3 years after PhD, I done a lot of work on various metal oxide and various carbon material for energy storage applications. Yeah.
So in these particular systems, we have already examples of manganese doped with other metals.
Yeah, definitely doping and functionalization, this material definitely will enhance the storage properties for this material. Yeah, definitely.
Yeah, yeah. And like I was saying in the chat to Rana, with my materials, with MOF materials tend not to be conductive. I mean, we can look to some mechanism with the delocalization of the electron densities, some through bond mechanisms, but we would have to, and a lot of the examples we're seeing in the literature would have to dope to enhance the conductivity. And we have in the MOF materials the space inside the framework to introduce dopants and enhance. That's the beauty of these materials. And in material synthesis, doping is one such an awesome technique to improve the quality and the properties and to engineer the properties of materials. Okay, I am not seeing any other activity in the we should have some questions for Ibtihaj, I think, as a PhD student, ladies and gentlemen. I think it would be good for her to feel some comments or questions on her work. I wouldn't want us to leave without engaging her. Ibtihaj, are you still with us?
Yes.
Yes. So I'm not putting you on the spot or anything, but I think when my PhD students and my students go out to a conference, an international conference, I would like them to come back with at least some exposure to some questions, colleagues? Does anybody have any comments, any questions for Ibtihaj? Given a few seconds. It's very rare that we have time. In fact, I could have allowed the speakers to go a bit longer had I known that there was one speaker who was missing. Most conferences we don't have enough time, and there's so much more we would like to talk about. I guess I was a bit distracted there for a moment, but I don't think I missed any comments. Did I, Prof? In the chat?
I'm checking also, so no extra comments or questions on the chat box or even Q&A.
No, I'm not seeing. So Ibtihaj, I'll possibly ask. I don't know if I missed it, but in terms of the green chemistry in your country and in your university and the industrial viability of green chemistry, can you tell us about the attention that green chemistry is getting in the academy, in the university, in the society, in government? You know, is it something that gets a lot of attention through public information or funding?
Yes, of course, green chemistry is a very important thing now because it is reduce the toxic and the effect on the environment. Maybe in chemical reaction, we know if we use reducing agent or oxidizing agent uh, during the reaction, maybe toxic material produced, and this is effects on the air pollution and effects on the environment. So green chemistry reduce the toxic, and it is more eco-friendly process.
Right, and I guess in your parts of the world, colleagues, your countries are oil producing countries, and so that's what I was reaching. Is there a lot of funding available for green chemistry work?
Yes, in my country, I think the chemical reaction doing by using, of course, green chemistry, because it
Wonderful.
is also economic process.
Yes. So, and have you tried different solvents? Because in the reaction you had your benzophenone was dissolved in IP. It's isopropanol, right?
Yes,
Yeah. Do you have an effect there if you in different solvents?
different solvent. This is in control experiments, because in control experiments we don't use benzophenone, just the sensitizer rose bingle in isopropanol. If we use benzophenone, the change in color happens. The solution from pink converts to colorless. But at the absence of benzophenone and the reaction exposed to sunlight to the same time, 4.5 hours, the color is not changed. This is due to the effect of benzophenone. But in another experiments, we change the isopropanol to water
Ah,
because we focus on isopropanol as a part of photoreduction of benzophenone to prepare benzopinacol.
yes.
We focus
And
on the change of solvent. After 42 hours, we see change in color from pink to pale pink. This is maybe change in major happens.
yes. And then also you are producing acetone.
Yes,
Yes, which you can then use in other processes.
yes, in another process like a
Wonderful.
solvent.
Wonderful. Well, colleagues and audience and speakers, I think we should, if there are no more questions or comments, I think we can bring the session to an end and we can get an early start on our next session. So at the end of that, I would like to thank all the speakers in this session. I would like to thank Professor Goma Ali for an enlightening discussion and for the work that he continues to do in his country. I also accept your thank you on behalf of my country here in Jamaica, and it really was a pleasure for me to meet with all of you. It is indeed sad that we can't be together over there in your beautiful country in Iraq. And I would like to especially thank Ms. Ibtihaj Subhe, who is our young PhD student in this session. I thank very much the audience for tuning in, those of you who are on Facebook and other social media platforms, and those of you who joined the session on this platform. Particular thanks to those who contributed to this robust discussion, and we wish you all the best. We thank the organizers of this World Forum for Women in Science, Women in Science Without Borders, and the colleagues there at the university in Duhok, Iraq. Thank you once again for tuning in to our session, and we wish you all the best. Do keep safe.